Okay, I'm going to present sort of a pragmatic approach we followed to check contract between interface specification and implementation. I am Dharmalingam Ganesan, and Michael Lidwall, who is not here, is my supervisor. I work for Fraunhofer Center in Maryland. We come to this flight software workshop more or less every year since 2005. So today I'm going to talk about NASA OSL as a case study, so I'll give a brief overview. And then I move on to static equivalence analysis and contract checking. You will see why we need this kind of analysis in this project. And then I will draw some conclusion. OSL stands for Operating System Abstraction Layer. So it abstracts something. In this case, it's operating system and underlying hardware. It isolates flight software from real-time OS specific APIs and hardware details. So there's no hardware dependency or OS dependency if you look at a flight software module. I'll show you the architecture in a minute. Implementation is offered for real-time OS like RTMS, VxWorks, and also POSIX standard. Basically, similar to Java's principle, write once and run everywhere, but at a compile time level here. So it's a fantastic idea that you can just select, configure a switch and say, compile the code for Linux. Then it will only compile the Linux specific folder, and then the high-level layers are completely decoupled from other details. It's being used in many NASA missions and as well as in APL missions. It provides support for really low-level details like file system, creating a file, opening a file, deleting a file, and so on, and managing tasks like create a task, delete a task, and so on. Queues for communication and semaphores, interrupts. All the very low-level details are abstracted in this OSL API. That basically, there's an interface documentation, and there are multiple implementations. Okay, so I don't have to explain why it has to be bug-free, but just for completeness, I will quickly walk through this. Flight software is mission critical, we know that, and it has to be of very high quality. And OSL is the foundation layer for the core flight executive, which is the NASA Goddard's open source software, actually. In the recent years, it has become open source. I was told that they made it open source to share software between different NASA centers. So it's interesting. And OSL itself is used in many NASA missions. For example, LRO and other missions are successfully using it. So the issues in OSL should be avoided as much as we can. So if there are failures on the OSL level, it will affect the high-level layers because it's a layered architecture style, similar to what Katie has talked about this morning. Here is a big picture of NASA OSL. So we have at the highest level layer a lot of applications. CFS stands for Core Flight Software Applications. And they are all independent of each other, like the previous talks. They don't have any compile time dependency. They are communicating via a nice publish-subscribe architecture that's facilitated and supported here at the software bus. If I can move the mouse. Here is the software bus. Software bus is basically offering a pub/sub API. One can publish messages. One can subscribe to a certain message. Application A and B can communicate indirectly with the help of the software bus. The core layer is basically core flight executive layer, is compiled together on one shared library. Applications are separately compiled and dynamically invoked at load time. The core flight executive has executive services who start all the applications one after another, and the applications communicate with the help of the bus. And there are other services that I will not talk about. There were previous presentations on this architecture, more detailed than what I'm talking here. Today, I'm mostly focused on the OS abstraction layer, and it includes BSP, the board support package, as well as the hardware abstraction layer. which, as you can see in this picture, abstracts away really low-level details like real-time OS API, board support packages, and device driver details. So there's a remarkable relationship between this architecture style or layered architecture and the previous presentations that talk about components being independent of each other. Here is another example where components are independent of each other and they communicate with a nice bus interface. All right. So let's go into the details of OSL API. OSL itself is basically offering low-level details, right? And OSL API is basically a bunch of header files. There are no any header file connection to Linux header files or real-time header files, whatever. OSL API is very generic, okay? And the real OS implementations are happening at the wrapper level. There's a POSIX wrapper that will, of course, use the Unix header files or POSIX header files. And there's a real-time OS wrapper that will use real-time header files. And there's a VxWorks wrapper that will use VxWorks header files. And, of course, they implement the logic that's specified at the OSL API level, right? So the high-level layers, in this case, apps or tests, are basically programming to the OSL API. And if you decided to use today VxWorks for some reason, you just tell the OSL build process, compile the source code for the VxWorks wrapper. Now only the VxWorks wrapper will be compiled. So the rest of the code will not be even compiled. And the high-level layer is completely agnostic, right? It has no idea. For example, you're writing an app. It has no idea that it's going to run on VxWorks. So that's the idea of this separation of concern and very well modularized architecture. Okay, so this is good, but there are a lot of problems now to handle from verification standpoint. We can't escape from testing and verification. There are new types of problems coming, whatever new architecture style we tend to choose, right? So one question is, how are we sure that all the wrappers are equivalent to each other? You know, can you really claim that the VxWorks wrapper is same as the RTMS wrapper? Because what will happen today if you are testing the software with the POSIX wrapper in your lab, and you wanted to tomorrow run it on real-time OS wrapper, how are you sure that the switch is safe? How are you sure that the behavior that's offered by the POSIX wrapper is equivalent to RTMS wrapper? That's not easy to verify, right? And that's one of the analysis activities that I'm going to describe today. Okay, so what I call that is statically checking equivalence analysis. Okay, so currently OSL has implementations for RTMS, VxWorks, and POSIX standards. And it is the argument that all implementations should work the same, meaning tomorrow you can choose this, and day after tomorrow you can choose some other wrapper. The behavior should be the same. So there's a standardized API, right? So we should be able to somehow check whether this is true. For example, can we check whether all the error codes that are coming from different wrappers are the same, or are there any discrepancies? Okay. So what we did was we come up with a very pragmatic approach, meaning we don't really do sophisticated formal analysis yet. We don't discourage the usage of formal methods. Of course, it's very powerful. But to start with, you always want to do something very quick. So what we did was we said, let's use a very simple pragmatic approach where we will compare textually whether the return codes that are coming from this wrapper is present in another wrapper. If there are return codes, for example, file length more than maximum. If it says file length bigger than the maximum is coming from one wrapper, and that return code is never coming from the another wrapper, then you're sure there's something is wrong. Maybe the developer who has programmed that wrapper has forgotten to check the max file length. You know, so very, very pragmatic idea. Just collect all the return codes from each implementation wrapper and do a set difference, basically. Check whether the set of text return codes that are coming from one wrapper is equivalent to another wrapper. That's the key idea of this pragmatic analysis. Okay. So for example, what we have done is we developed some kind of a very simple editor where we could compare visually differences between implementations of wrappers. Say, for example, you see here, POSIX implementation has, I don't know about that. OS mutex semcreate, which is basically creating a mutex lock or something like that. Of course, it's the same signature, right? It's in the POSIX side and also in the RTMS side. Same signature. That's the idea of the OSL. Otherwise, there's no OSL. It's the same signature, but different implementations, right? And in this case, for example, you see this code will return OS error, and this code will return OS sem failure. So there are two different return codes coming from two different wrapper implementations. And this is one simple example to show you that there are some subtle differences. Maybe one day semaphore create will fail, and that day the high-level layers may misbehave, right? Because the error codes are different. I also want to say that the constants for OS error and OS sem failure were also different, which we checked that, of course. Even if the constants are the same, why would you have two different error codes for the same reason? So this is very simple, right? You just grab for return statement. And the first prototype was very simple, grep-based. We did a grep on a return statement, grab all the data, and we have a database of error codes that we could cross-check. The tool is a prototype tool, actually, allows us to visualize the differences as well. You can see that it aligned and shown the difference at the return statement level. Okay. So what we did, I'm not going to read all this table, of course. What we did was we were able to collect this kind of table in a semi-automatic way, just leveraging the naming conventions. If you know the naming convention of the return code, you could use that to write your regular expressions for your grep statements, for example, right? And it's also nice. The OSL is pretty well documented, so we were able to leverage the OSL header files where they explain, okay, if you pass a null pointer, this is the return code. If you pass a file name which is more than this, we will return this. So this is a bunch of return codes are well documented. So we could more or less write a simple regular expression to extract all the documented keywords of return codes and compare it with implementation in fairly automatic fashion, actually. So what we have done is we collected this table. We can now compare whatever favorite tool, Excel or whatever, can be used to compare. Okay, is there a return code OS error coming from OS API.c on a particular function? If there is nothing, then we say there is something wrong between one implementation in comparing to other. We don't know which one is correct because we don't know what is the golden standard here. We're just cross-checking one wrapper implementation against another. And you can see that there are a lot of holes there. That means there are places where things were not consistent to each other. So it's helpful to discuss further, and often the case it's a bug. The developer has forgotten to add a new feature, or it's a copy-paste error. Sometimes there's a lot of overlap between the wrappers, so they might have been simply copy and paste, but forgot to either update the document or update the return codes. Then that's the major reason why we see something like that. Okay, so what kind of defects did we find in analyzing the function pairs that like we did? Well, we could find differences in precondition checking, meaning one implementation will check for if you pass a file name which is lengthier than the configured limit, another implementation will not check for it. Or one implementation will check for your pointer's correctness, another will not check for it. So it's kind of precondition checking. And then return code differences like we talked about. And then since it's a wrapper based on a standardized interface, we should be able to figure out what are the variables being updated, the global variables being updated by each wrapper. We could see in some implementations certain variables were not updated, and others that were updated. So state-related differences were emerging. And then some parameters were checked, and some were not checked, that kind of differences. And there are some minor differences like printf or log messages were different in different wrappers. And so we were able to fairly get hidden issues without doing much modeling work in this project. Actually, in 2008, we presented how we really checked whether the architecture is followed by the implementation. I shown you the layered architecture with different layers, but how are we sure that implementation is still layered? We have to do real checking, actually, and there were some interesting differences, but overall it was a consistent architecture, very, very, very well done architecture. In 2000, 2011, I believe. Yeah, 2011, we did model-based testing of WOSL. One of the layers were tested. In that case, we have to explicitly develop a model. We developed a model of the API. We derived test cases, and then we compare against the implementation. This work is slightly different. We don't do modeling. We just leverage the naming conventions and write very simple, pragmatic scripts that does the job for us. Okay. All right. So next, I'm going to talk about contract checking. What is that? APIs are supposed to fulfill a contract. You know, if you see a header file, functions are documented in some form, right? And that's a contract for others. Okay. If you use my implementation, this is the guarantee I provide to you. That's what the contract says, right? But it's very difficult to check really whether implementation is satisfying the contract. I have been trying to do some sophisticated methods. They're very powerful. There is nothing against them. But it requires a fair amount of work in developing the specification itself. In some cases, the specification looked more complex than the implementation, actually. It was like very simple things like if you are checking whether a linked list is really a linked list, or if you have a function to reverse a linked list, it's so difficult to specify it precisely. It requires more work to write the specification anyway. But it's helpful to have a specification like that. In this case, we are not doing that. We are saying let's stick to the specification that's textual there. We just grab the error codes and we check whether implementation satisfies. What are we doing here? We write some very simple scripts for that. Let me show you an example first. Here is a simple contract. It says, delay a task for a specified amount of millisecond, right? That's what the contract is. And it says, we will return OS error if something happens and success otherwise. So there is a contract and there is an implementation. So it seems to be satisfying. I mean, we can see that there's an OS error and OS success, at least. The contract doesn't say a lot of details, but let's keep this as an example, okay? So we can grep, if you will. We can do a text matching, say, yeah, okay, there is an OS error in the header. We can find a OS error in the implementation. So it seems to be okay. Again, it's not so solid, but we're just trying to figure out if there are any discrepancies. And then here it says, yeah, there is a OS success. Do you find a OS success? Yes, I do find somewhere in the implementation. Okay. And look at this one. So you know where I am getting now. There's an example of a function not fulfilling a contract. Here it says, return information or OS error if a module ID is invalid, OS invalid pointer, and OS success. I think we don't see that. We don't see where OS error invalid ID is, right? This particular text is not there in the contract, right? We don't see OS underscore error underscore invalid ID. So there is something different. At least there is some discrepancy between what is specified in the header and what is there in the implementation. So we can bring up this for discussion. We don't claim it's a 100% guarantee that it's bug-free, but we can bring it for discussion, right? Okay. So what we have done is leveraging the structure of the comment, write some little programs and then extract all the return codes from the function bodies and the contract comments. So you can imagine now I have two databases. One database is return codes of specification, another database is return codes of implementation. So now I can do a database query, right? Okay. So we compare the return codes of contracts and function bodies to find mismatches. Okay. So what do? We just get this little database where we can see file, what are the file names, what are the functions defined there, is it present in the comment but not in the code. That means it's specified as part of the contract. The system will return sem failure, for example, in the OS binary semaphore create function, but it is not there in the code. So this is very simple. Then we give this database to the developer, and he goes through it, and he reasons about it and says, yes, this will be fixed in the next release, and so on. So this is what we did in this part of the analysis. Okay. But then there's another thing. What about functions that implement more than what the contract implies? There could be more return codes emerging in the code that's not there in the specification, right? it's the same thing, but it's looking at the different angle. Okay, so we do the same analysis. We check for return codes from the function bodies and look whether it's in the contract comment. It's just a regular text matching. Okay. So for example here, we have file system error invalid pointer. We can trace it. Error path invalid. I think we can still trace it. Path too long. Yes, we can trace it, but we can't trace the file error, right? OS_FS error. So we can find some more behaviors that's in the code, but not in the contract, right? Because there's nowhere in the contract this particular OSFS error is discussed, right? These are the only 3 types of errors that were discussed. So we could just say, yeah, okay, there is a hidden error code here that may come out at some point. Okay, so why does this work? I mean, this works for a couple of reasons. One is there is a uniform template followed for the contract specification, and there is a naming convention. So we could leverage those two to make this happen. Otherwise, it won't work on any ad hoc system, unless you do precise modeling for your requirements, and then you can check some of them at least. Okay, so how many issues that came out? Well, we were able to find 61 such issues actually, and all of the issues were reported and taken care by the OSL developers. And it was pretty neat that we could get with the help of just regular text matching. Okay. So to summarize my talk, we have a technique that can compare different wrappers. If the wrappers are supposed to behave the same way, you need some way to check that. And here is one very little lightweight technique actually. We say lightweight because there's not much investment from modeling or sophisticated formal work. Powerful for detecting inconsistencies. We don't claim that we detect all of them, of course. There were many more that we think were still lurking, but we couldn't detect. And several inconsistencies were detected actually and addressed in OSL already. And another analysis was this contract checking to check whether contracts are satisfied by the implementation. This is also very lightweight. And very quickly, one could find a lot of inconsistencies between documentation and code. In this case, it means the high-level layers